Yes, sir, loud and clear.
So let me project my screen. And once you ask me to get started, I'll get started. Okay. I think let's wait for some time. Let's wait for a critical mass for 10 people to join, and then we should get started. Okay, seven people have joined. Let's just give it 1 or 2 minutes more and start it. In the meanwhile, what I'm going to do is in the chat window, I'm just going to share this particular folder to help you with the codes and everything, right? Okay. In the meantime, Mr. Pranjay from Upgrad, I'll request the host for this particular session.
Done, sir. I've already given you the co-host access.
Great.
Yeah.
So yeah, I see. So they have joined Raj, Farha, Kaushani, Sayanti, Saurav, Snehal, Vikas. Good evening to everyone. I hope you have got links, right? Please download from that particular link. Some of the things that we'll be doing, there is the link. Okay, okay. So my bad. Actually, it went to the hosts and the panelists. Yeah, let me. Now I hope that the screen is visible. Right. Now I hope that it is available to everyone. Just download the code and the dataset from it. Okay, today what we are going to do is one, some part of the piece which we have not done yesterday. Maybe we can do that. But first, as promised, I'll start off with the hands-on part. This main focus be the hands-on part, and all the other parts, all the other things, be pretty one thing. This is the most hands-on part. I'll just keep the videos off. Okay. Okay. Everyone downloaded particular files. Everyone downloaded. Okay. So let's get started. The first piece. Right. So let me once again share my screen with you. Okay. Pradna is saying that you have just joined. Not to worry, Pradna. Yeah, I'll just paste it here right away once again. Right. Okay. So in the meantime, what I'll request the learners is that as and when people are joining, maybe we can just pause and just paste this link chat from time to time. People can. Okay. Let's get started. Right. The first problem that I'm going to do today is the one which talks about an imbalanced data set. So you'll find that in the data set, there is something called as this breast cancer. It's a very popular data set, and what it is having are some parameters, like basically parameters of the tumor and all those things. People who had suffered from cancer and the breeding also for the same. Right? So let's open that particular data set. That data set you'll find in the folder called breast cancer. Right? And here there is a CSV file. It says data underscore updated. So what has happened is that I mean, from a different file where the raw data was there, this data has been converted to a format which can be easily imported and used in our models. It is a very classical and popular data set.
The learners are saying that your screen is not in presentation mode.
I'm so sorry. I'm so sorry. Okay. This is the data set I have been talking about. As you can see, there are about 457 rows of data is what we have out here. And if you see the columns which are there, the thickness of the lump which is there, the size of the cell, right, whether it's uniform or not, shape, then the marginal adhesion, single epithelial cell size, bare nuclear size, chromatin, I don't know what that is, normal nuclei, metastasis, and the spinal class. Class is the one it's imported, right? We can here it specifies or signifies that with this from a malignant version of the cancer or not. Right? Now let me project my screen to you. Okay. So yeah, my file escaped in the Google Colab. So I constantly use Google Colab. In fact, the piece which I've also given you, that's also there. So again, whenever you're using the file from these codes, make sure that you have created the folder in this particular structure in your Google Colab. Otherwise, what will happen is maybe you have to specify the location at some other place. In the Google Colab, what happens again, whatever is there in your Google Drive, it gets mounted. And then in the mounted drive, what I have done is I have created a folder which is called Colab Notebooks. Under that, there is something called dataset. So that is where data files are there. And here under dataset, you can see this breast cancer file is there. Right? That's what we are going to. Okay. The data which I'm going to use is the one which says data updated. Let's import that. Okay, and this is what we see. This particular data is having 456 rows and 10 columns. That's what it is having. Right? If I would just like to have a look at the data frame, what it talks about. So data frame dot till, something which will give you the last few rows of the data. If I would just like to probably take a sample, let's say a sample of 20 from this, just write sample and then 20, and this is what it will be, right? So random sample of 20 values from this particular file. If I'm looking at the information content, that's particular data frame. Data frame.info is going to give me some information about the file which I'm dealing with. And here you'll find that I have 10 different columns. And by the way, all the columns, they are numeric. All the columns, they are numeric. My question to the class is that the objective which I have out here, find out whether a particular tumor is malignant or not. In that particular case, what do you think? That what should be the data type for this particular class? What should be the data type for this class? Answers are coming. The object, or again, you can also take it as a category. I think some more people have joined. I am once again pasting the link, the code file, as well as the data set which will be used. Right? One thing which I can see, that there are no null values out here. There are no null values, right? So in that way, I don't have to do any kind of a data cleaning. I can directly go on. And once I run my value count from the classes, what I see is that for the type 0, which is not malignant, there are 244 rows of data. For the class 1, which is malignant, I have only 12 records. Now, you know what the problem is. Because 12 records are so few, right? The value, it's about 2.5% of the entire value of the data set. Only 2.5%. Right? So if you try to create any model from this, what will happen is, because class which is of type 0, that is mode, will always be biased towards detecting the non-malignant data. Right? Data imbalance. Okay, questions to the class. Can you give me some more examples of data set, common data set, where you can find this data imbalance? Anything that comes to your mind? Anything that comes to your mind? Okay, some answers are coming in. Fraud detection, great. Yes. Fraud detection is something where also you find a lot of data imbalance issue. Good, good. Right. Anything else? Anything else? Even like spam detection, not really, not really. Spam detection, if you think about it, I mean, just open your mailbox tomorrow morning. Count the number of spam mails that you have got vis-a-vis the number of voter ID cards. I did not get this point, Raj. Can you just explain what do you mean by this voter ID cards? You're actually asking about class imbalance kind of things like there. Voter ID cards probably not be the case. Anyway, spam detection will also not be the case. But yeah, fraud detection, credit card frauds, all those things. Those are probably some areas where there is a lot of data imbalance. Right? Okay. So let's prepare the data. Let's prepare the data for modeling. And for this particular part, we are just taking the data in a new data frame. After that, the first thing that we are going to is probably try to have a visualization of this particular class. This is what it looks like, right? Obviously, you can understand that this is not something which can give us result. Then in that case, what to do? Maybe in some way or the other, we will have to make sure that this particular data in a shape by some analysis can be made out of this. Now, this particular library, IMBlearn, right? IMBlearn stands for imbalance learning. Right? So from this IMBlearn, what we are doing is we are importing this particular sub-library which is called SMOT. Anyone knows what's the full form of SMOT? One SMOT. Then the async content SMOT. SMOT. The full form of SMOT is synthetic minority oversampling technique. Synthetic minority oversampling technique. That is what SMOT stands for. And then one of the commonly methods for the imbalance problem. See, let me tell you something. For basically working with imbalance data set, there are many different strategies which we spoke about yesterday. One of the strategies was undersampling. The other strategy was oversampling. If I do a undersampling, what will happen is that maybe what I'll do is for the class which is lesser represented, I'll have to get my data part right to a point where it matches that particular class. But here my minority class is 12 records. 12 records, very difficult to get 12 very distinctive records from the majority class, which is again other part not malignant, and then create a model from that. It's probably not the best action that we might be doing out here. So for that reason, here we are trying to use the SMOT library so that we can oversample the one which is underrepresented. So by default, what it will do is it will try to match with the number of records which is there in the majority sampling. But otherwise, what you can also do is you can also give some kind of a percentages. So then in that case, it will oversample to that particular percentage. Let me show you that. So, okay, here these are the libraries which I'm using: Pandas, NumPy, right? The Smoot library, and this is basically the random number generator library. Decision tree classifier, random forest classifier, accuracy score, precision, recall, F1 score, confusion matrix, and again these are the different model selection techniques: train test split, cross validation predict, and this stratified K4. These are some of the things which I'm using. And here the first thing that we have done is we have defined this particular function called matrix. So what will this matrix function will do is that as long as you're able to supply the actual value and the predicted value, it will bring out the accuracy, the precision, recall, F1 score, as well as it will draw the confusion matrix for you. This is what this particular library is supposed to do. And you can see from the top that in this sklearn.matrix, that's the library. So there we are importing the accuracy score, the precision score, recall score, F1 score, and the confusion matrix. This is where it will probably get, right? And once you pass on the scores for the actual value vis-a-vis the predicted value, what will happen is that it will give you the values for this particular metric. My bad, phone is ringing. Just a moment. I'll do. Sorry, my bad. Okay. Once this particular function is defined, let's create a baseline model, right? This is the baseline model that we are going to create. By the way, my features will have all the values except the class value, right? That is what will happen in the feature part. And for the target, the class, the only variable which is there, right? We have said that the test size is going to be 30%, right? And then stratify equal to, anyone knows what exactly this particular part does? Or rather, let me do one thing. First, run this without this particular part. Anyone knows what this stratify does? Anyone knows what this particular stratify does? Quickly. Anyone? No one? Okay, some answers come in. Okay, so Saurav is saying equal proportion select, Raj is saying no. If you remember, we had discussed in class that the case where I have a data set where the different classes that the output of the target classes, they are not the same. Right? Then what will happen is that randomly it might create it and create the data set. So let me just not use stratify and let's see what happens. Okay, my train data and this is my validation data, right? 30% of the data has been used for training, and 30% have been used for validation and 70% for training. Now, if I basically do a hold on, I think I'm getting the command wrong. So What's happening? The not will why? Train, y underscore train and y underscore valid. Okay, these are the two things which we have. Okay, what we have, right? Another part, normalize. This will give me the corresponding percentages, right? If you see the zero class is 96%, multiply 100 with it, and the one class is only 3%. Similarly, if I do it for the other part, the validation data part, right? This is what we'll find. The validation data, there is 99% of zero class and 0.72% of the one class, right? That is what we have, right? Not fair. That's why what we are going to do is we are going to use this stratification, which will ensure that in the training and the validation, the proportions are the same. So once we run this, then let's see what is there for the training data. This is what I have for the training data, 97.49% and 2.5%. And I'm pretty sure that the same proportion will be here for the validation as well. Right? You see out here that it's almost the same proportion. See, 2.50 and 2.91, right? Doesn't make too much of a difference because again, the numbers are so low that probably the distribution was one of here and there. But again, this is what it is at this point in time. How training and the validation data has been created. So at least the proportions have been maintained once you have specified the stratified thing. Had you not specified, then what would have happened? Already seen one of the cases, there was almost a 3.5 to 95.5%. And in the other case, it is 99.3% and 0.7%. That was what it had happened. Right. Okay. Now let's do one thing, that random forest model which we have created out here. So random forest n underscore estimator is equal to 10. What is this n underscore estimated random forest? Anyone knows? N underscore estimator is number of estimated, or basically the number of trees that the random forest would have created. Right? I think Saurabh has given the answer. Great. Okay. So this is how my confusion matrix looks like. Right? So for the zero class, 133 is what we have as the true positive, and for the other class, we have 1 as the true negative. Let me also see before this thing numbers that we had. Numbers that we had for the validation. Okay. Okay, so 4 data points were there. Again, of which only 1 has been correctly classified. All the 3 have been misclassified. Right? All the 3 has been is classified as low class. Right? And as I told you that it has typically happened because the number which are there very good. If you see accuracy in this particular case is coming as 97.8%. Why? Because 0 is the majority class, and by default, if it would have said that all the data points were 0, then also the accuracy would not have changed too much. But come to like recall and the precision. Precision says 100%. How is precision calculated, by the way? Precision, how is it being calculated? Calculation. Precision calculation. Right? Don't remember? Okay. So precision was simply about of all the data points have positive, how many of them are actually positive. Right? Here, if I see the precision for this is 100% because again you have created 133 data points as this thing is 0, and all those 133 are actually 0. If I talk about the recall part, right? If I talk about the recall part, what was the recall? What was the recall? People are saying my voice is breaking. Is it happening for everyone? Is the voice breaking for everyone? Let me just voice should not break because the video is off. Is the voice breaking for anyone else? Okay, let's find now. Okay, fine, wait. Coming to the recall of this model. The recall of this model for the class which is one class, right? In the one class, what is happening is that actual value of those people with one with those lumps, that's 4 in number, of which only one has been correctly identified. Of a total 4, only one has been correctly identified. So that's why here the recall is coming as 0.25. See, rather than this particular part we are using, right? So there is also another library. We have used this library out here, which is the accuracy score, precision score, recall score, F1 score, and then confusion matrix. We also have another library, which I believe is classification. It is called classification report. Rather than all this, I can just comment this particular part. Can just use classification report, and here you have to give the and the threads. That's one you have to feed, and let me print this so that it will give you out the result. So yeah, okay. Once this is done, let me just run this particular part. And this is what we had. And let's check the result with the previous one, then we'll check the result here. Okay. Here, opening classification report. I think we have not find it. To run it once. Now it should run properly. Okay. Okay. Here is what the result shows up. For the class 0, the precision is 99%, the recall is 1, if one score is 1, support is 136. For the class of 1, here, basically all the metric they are 0, 0. Because again, I think only one data point was there in the class 1. But again, this particular case where we had done the stratification, here you find that again the result should be some tad bit better compared to the previous one. Okay. And now if I run this, okay, here is what it is. For the 0 class, the precision is 98%. So I think Saurav was coming out with 133 by 136, right? So yeah, that is the part which is giving you 98%. For the recall part, it is 1, right? All the positive ones have been, all the 0 ones, they have been correctly identified. If one score is 99%, and support, how many data records were there? 133. For the class with 1, right? Precision is 1. Means that only one data point was predicted as to be this thing of class 1, and that was true. But come to the recall part, 25%. If one score 0.40, or 4 data points were there. This is what we see as the result coming out from this model. Overall accuracy is the 98%. Overall accuracy vis-a-vis the previous one, overall accuracy was 99%. Again, I think we had discussed this particular point, that why accuracy is not always the best metric which you should be considering. We're looking at the other metric which are there. Okay. So now coming down, as you have understood that this was probably not giving you the best result. So let's try to oversample the minority class. Okay. Question is asking, can you show once more how you got the accuracy and precision with the confusion matrix? Okay. Question is, I mean, it's there in this particular file which I've shared with you. Yeah, the only change which I did was I used this new library called classification report, right? And this classification report will give you all the values for the defined metric which are there. So we have just printed the classification report where we have passed on the value of the actual values versus the predicted value. That's what we have done. Right? Fair enough? Let's come down. Where were we? Okay, this was where we were. And now, as I said, that what we are going to do is we are going to oversample the minority class. And you see that right now 622 data records it has got created, right? The minority class have been oversampled, and then how the data looks like. 0, nothing has been done with it, but 1 has been made match with the right. Oversampling has been done. And then right now, let's do the same thing which we did earlier. oversampling part. This is what I have done with the data, a random forest classifier, where, by the way, I have used this cross-val score. What exactly is cross-val score? Cross-val score is coming from that cross-validation. Cross-val score is done by cross-validation. In the cross-validation, what I have passed is the model which I'm going to use. Here in this particular case, it is the random forest. And then X is the value of the features, Y is the value of the target, and scoring, which we have said, the accuracy. That's what we are going to take. And these are the results, what is coming out: accuracy, precision, recall, and F1 score. The water coming out, right? Some question. Okay, Saurav has an interesting question that has it been created just by repetition, means with replacement, right? It's a that you have asked. If I had to just take up this thing, this oversampling by simple sampling, what I could have done is I just have sampled the minority class and could have matched that with the majority class. That was pretty easy. I'll show you also how you can do that. That raised this particular question. So we copy this particular part. Okay. What I'm saying is that what Saurav is saying is that is it simply sampling? Not really. Here I'm passing the X underscore train it. Okay. So in the X underscore train, I am not the X underscore train, my bad. Basically, my Y is where target variable is there. Basically, what it means is that I'll have to probably oversample Y more times, create some kind of a confusion. I'll just tell you. What we need to do is we need to oversample the class where the Y value is 1, that it can match the 0 value cases. Right? Asking, we can't see the other questions, messages. I think again that is some kind of a setting which the meeting has been created with. I don't have any control over that, unfortunately. Right? How the meeting has been created. Okay, so coming back, what Saurav's question is that is it only some kind of a randomly oversampling? So what I said is that it's not really a random oversampling. In the random oversampling case, what we could have simply done is that the instances where the Y value is 1, we probably just could have oversampled it. But in the case of things like this, synthetic, that's why it's saying that it is synthetic minority oversampling technique. In this particular case, what happens is that actually try to create data point by mixing and matching the traits of the data in the minority class. Rather than creating verbatim data points, some data points are very close to the actual ones. The other ones, what you do is you basically use sampling technique to sample the features and create poor features which are very close or similar to that of the existing. So if you remember the KNN algorithm that we had learned, almost similar to the KNN algorithm in some cases, right? We are trying to create data points which will be very close neighbor of the original data point, right? And once we have done this, what we see, the data is balanced, and now what we are doing is we are doing a cross validation score. And this time you can see that what are the values that you're getting. The average accuracy score, average recall score, average precision score, as well as the average one score. That's what we get once we have done the oversampling part. That is to do with the performance. And if you remember, we had also spoken about the model stability, that how stable is this particular model. So for this, if I just run the standard deviations, what the standard deviation says, right? For the accuracy part, the standard deviation is 0.009. For the precision part, standard deviation is 0.017. The recall, almost 0. And for F1 score, standard deviation is 0.9. So pretty consistent records. Pretty consistent scores is what we'll be having. What you can also do is that sometimes, rather than using a CV, by the way, CV stands for the cross validation. Here I am doing a 5-fold cross validation. Let's do a 10-fold cross validation. 10-fold cross validation. Okay. So in the 10-fold cross validation, see that the results have not changed much. Otherwise, even for other pieces, okay. By the way, here we see that the standard deviation has increased a little bit. Can you see that? Compared to the earlier ones, the standard deviation has increased a little. Isn't it? Okay. What will happen? My question to the class. What will happen if I take the LOOCV? If I take the LOOCV, how many splits will I be making? For the LOOCV, how many splits of the data will I be making? N. So let's say what's N out here. So here we have N as 622. Let's do that change. 22. First is 622. 622 and 622. Let me do one thing. Let me just copy this particular piece. One is the part where we are doing the LOOCP, right? And I'll also do something else. On the run, we are changing some of the things. For time, start equal to time dot time, and then end equal to time dot time. Print elapsed time is end minus start. Hope this will run. Let's see. Then some error. In split secure can configure the number of members in each class. It has given me some error. Now, can't be more than the number of members in each class. Why? We have 622 records, right? Is it? That's what it says. 622 records. Number of estimators. We have taken 10. Cross validation score. All this is fine. I think it should have run. Should have run. Not sure that why it is giving this error. Ideally, it should have run. It should have run. Because here, what I'm doing is the cross validations. We are creating the same number of records as. Just reduce the number a little bit. Giving some 600 can't be greater than the number of members in each class. Number of members in each class, it should be 622, right? I mean, that's what we were trying to do, but again, somehow it is not working. Not working. Should have run with this one. Anyway, bit much, but yeah, what I'll do is I'll probably increase the number of cross-validated score out here. Now it's running. Now it's running with a lower number. You can very well see the amount of time that it is taking, right? Each of the cases. 13 seconds is what it took as the elapsed time, right? And this time, if I also compute the standard deviation, find the standard deviation also be relatively higher. So you see out here 0.027, 0.044, right? 0.0244. Vis-a-vis here, we had used the number of estimators. Let's say here cross validation 5 we are going to use in each of the cases. 5, the original one which was there in the data. And if I run this, first of all, you can understand that time taken was much lower side. And also standard deviation, also you'll find that it is pretty much low. Remember, we were discussing yesterday that in the case of a LOOCV, what happens is that as and when you increase the number of folds, more partitions, the standard deviation obviously will also increase more number of folds, right? Okay. After this, let's do the prediction. The model that we have just created. Here are the accuracy scores: 99%, recall is 1, precision is 98.73%, and F1 score is 99%. Using this oversampling, we have actually come part where works. What is that? Okay, I think I'm using a different version of format, but yeah, I mean, this was the part to which we wanted to keep it, right? It's pretty okay at this particular point. Let's do one thing. Let's extend this to another bigger model. Let's extend this to another bigger model. So the next thing, find that I have given you some another data point, data set, which is called this bank marketing campaign. Have you seen that? Bank marketing campaign. The data set is the bank term deposit. Got that? Let me project my screen with you. Once again, here it's the classification problem once again. me just manage my session. Let's terminate this one. This one also I'm terminating. Okay. What we are going to do. Once again, here also, particular part, the classification problem that we are going to work on. And there are a lot of steps also here, like almost like a real life project that you might have. There are parts when probably you'll have to work with the dirty data, trim it, clean it, all those things you'll have to do this particular file. Like usual, what we are doing is first the pandas for importing, NumPy for making numerical calculations, Matplotlib for doing the plotting part, Seaborn also plotting, and SciPy has some of the statistical modules. Let me first execute this one. It's running. Okay. And then once again, I need to give the permission to my Google Drive. My files are there in the Google Drive. And to give it a permission. Okay. Then let me read the file. And this is what I have. It is having 41,188 rows and 14 columns. Right? That is what it is having. And then if I do a sampling from this particular file, sampling, just a 20 sample from this file, this is what it is. This is what is coming out. So these are the different columns which are there. Age column, the kind of job this particular person is doing, marital status, education, whether this person is having a car loan, housing loan, personal loan, right? How to contact this particular person. When was this particular person contacted? Month, day of week, campaign, right? The outcome of the campaign. And then this Y and N. These are basically the target variable which talks about whether this particular person is going to take some loan or not. Right? That is where it is. So let's come down. Let's come down. This is the shape. We have already got that. Let's first go and check for the presence of null values in the data set. Null values. As we see, there are no null values in the data set, which is a good thing. Let's find out the number of unique variables present in each of the feature. So for that, what you can do is dataframe.nUnique. So dataframe.isNull, that is going to give you the null values, and then you sum it up so that it shows you the aggregate number. And this nUnique, it will show you the number of unique variables present in each of the features. Age, job, marital status, education, car loan, housing loan, personal loan. So the unique features which are there. So that thing is going to show us. Right? Good till this particular point. So let's do a description of the different values. So age, campaign, and PDays. PDays, by the way, is from whatever I recall is number of elapsed days when this customer was last targeted for a campaign. Samrat is asking, could you please explain XGBoost and gradient boost theories at some convenient time? So again, let's do one thing, Samrat. Let's do this particular hands-on part. So today's class was to be the hands-on part, and then we'll have some time. We can take up some of those theories in that particular part. Right? Okay. Here we are renaming Y as the target. That is what we are doing, the renaming part. Right? And then here is once again the count plot. Once again, you see out here that the number of yes cases are lower compared to the number of no cases which are there. No cases which are there. Right? If I see the value counts, no is 88% and yes is about 11%. Come down. Data frame.corr stands for correlation. So what it will give is the correlation with the different numeric variables which are out there. Age, campaign, and key days. So these are the three numeric variables which are there. So one good thing that we see is that none of the numeric variables, they are related with each other. In that sense, there is not much of a multicollinearity that we see out here. Right? Some is okay. People are asking for XGBoost, gradient boost, and stacking. Okay, fine. Let's take it up some point later today. But okay. So now what we are doing is we are doing a box plot of the numeric attributes to check the outliers. Here, once I'm doing the box plot, as you can see, there are a lot of outliers for the age variable. Quite a lot of outliers for the age variable is what we see. Typically, again, when we are talking of things like loans, right? Loans are typically being taken by young people. There are quite some old people who are also there, the customers. That's probably the reason why we are having so many outliers values out here. Quite a few numbers are there, which are people who are very old, over the age of 70. Right? Okay. Come to the next one. So here the number of campaigns. So campaigns also you see that some of the customers, they were subjected to some high number of campaigns, which we see out. So which with respect to the overall data set is coming as some type of outliers. So we probably need to deal with these values. Also, what we are going to do is we are also going to do some kind of an analysis with the other ones, which are the categorical variables. So this was the numeric variable that we had. Let's look into the categorical variables as well. Looking into the marital status of the people. So you see that a lot of the customers were married for 25 per thousand. 10,000 were single marital, single status, and then about 5,000 were divorced. That is what we see for the marital status part. And then for the education part, this is how it looks like. So till this particular point, what we are doing are the basic EDA and the pre-processing. As I've kept on saying that this particular part is the one which will take a maximum amount of time for the data analysts. We are dealing deep with that particular part. This is the education part which is there. What we see is that sizable chunk of the people are having university degrees. Right? In the data set, there are very few or almost probably no entries which are illiterate, people who are illiterate. Right? Also, if we look into the distribution of the jobs, the people, right? what we see out here is that for the housemate part, right? Housemate, very small number of people are there. Services, lot of people are there. Admin, lot of people are there. Blue collar, technician, retired. So this is what we have. By the way, tell me something, right? This particular plotting that we are doing, the univariate analysis, this is giving me the aggregate information. If I would like to, based on the two different output classes for the target classes, how can I do that? Here, if you see, this is basically based on all the data. Is there any way I can bring in some more variations to it so that I can see both the plots at the same point in time? Saurav is saying joint plot. Okay. So how will you do a joint plot, Saurav? How are you going to do a joint plot? Joint plot? Joint plot, the one, how you are going to do? Numeric pair plot, that's fine, but again, how you're going to do out here? Let's try out. Believe you can use the color variable, color equal to data underscore frame target. Might work. Let me check. It's not working. Color, okay. Target is encoded as a number, and that's why it is not able to use. Let's see, it works this time. Valid values, invalid values is data frame. Did we change the this target, right? Yeah, we had changed target. Just a moment. Just small check. Ideally, this should work. This should ideally work. Just let me do a small check. Why it is not working? In the meantime, any suggestions from anyone? How we can make this working? Suggestions from anyone? How we can make this working? Some small this thing error. Okay. Or might be different. Called as a color variable. That be coming. Okay. Another way of might be just write frame target. This should work at least. Not. Mark is an empty sequence. Why? data underscore frame target. So data is data underscore frame, data underscore frame. I'm taking the target value as not sure why. Actually, some mistake we are making. Category variable. Or it is number only. Forget that. Again, come back. Not working, it will not work. Anyway, let's come down. Okay. So this is the other one, which is comparison of the different kinds of loans which is there, right? So for the personal loan, what is happening is that most of the people who have taken a personal loan, right? In this particular case, most of the people who have taken personal loan have not gone for those term deposit. Most of the people who have taken house loan, they also have not gone for term deposit, but people who are having car loans, right? For the car loan people, a sizable number of them, they have taken those term deposits. So again, this is what is coming out from the data visualization. I think now I know where the problem was. Problem was with the this thing, how we use the target variable. Target variable, I was taking 0 and 1, but here the target variable till this particular point is this thing. Was no and yes. I think that is where the problem was. Let me just retry once again. Doesn't happen to drop it. Yeah, that was where the mistake was there. The values were no and yes, not 0 and 1, which I was assuming. So again, this is what I see for the people who have not taken loans, and for the people who have taken loans, right? You find that a significant percentage of the married people, they had taken this loans. Significant percentage of the married people, they have taken these loans, right? Single is lesser. Divorced people, they were not requiring the loan. This is for the case of thing. Yes, and this is for the case of no. So again, like this, so what we can do is we can probably do it for the other fields as well. Not doing it, but yeah. Coming down, the target variable here has finally been encoded as no has been encoded as 0 and yes has been encoded as 1. This is what the value count coming out for the target variable. 0 is 36,548 rows and 1 is 4,604. So here is some kind of an aggregated value that we are doing. So for the job part, once I aggregate based on the sum, as you can understand that since 0 value are 36,000 and 1 value is 4,640, so the sum will basically reflect the cases where the person was had taken this particular loan. The job versus the term deposit counts. These are the people who have taken the loans, and this is what. So admin people, a very high number of those people, they have taken this loan, right? Followed by technician and then this blue collared people. As you can understand, unemployed people will be pretty low on the loan part taking. Same holds true for the people who are retired, they also probably not will be prone to taking loan. So incidentally, entrepreneurs, I would have expected that they would take more loans, but again, it's what it is coming up. They have not taken much loan, and housemates also have not taken much loans. By a value count for the job part, this is what is coming out. So admin people, right? There are a lot many number of admin people who are out there, right? So or 10,422, of which some 1,200 people have taken the, right? Almost, in fact, more than 10% of them taken the loan. For the blue collared, so we have 9254 blue collared people, and here we see about 600 blue collar people, they have taken the loan. So here also it is roughly about 6% of the people taking the loan. So like that you can do the analysis, right? Okay. Let's take the marital status. For the marital status, as we saw earlier, right? Earlier you saw that something which we saw earlier also when we did filtering by the marital status. People who took the loan. Here we see that for married people, those are the ones the maximum loan. But we see out here, divorced people did not require too much of this loans. What we have, and then we also seeing by the month, how does the loan figure looks like? It seems in the month of May, maximum people had taken the loan, right? December holiday season, this number of people had taken the loan, right? But again, what I would expect is that before December, maybe October, November, there should be some proliferation. So yeah, October, November, okay, we don't see much people taking the loan. Any reason why you think that in the month of May, people would be taking a lot of loans? Or making some kind of a term deposits? By the way, my bad, it's not the loan, the term deposits. Term deposits, why in the month of May, there's a lot of term deposit? Why in the month of May, there's a lot of term deposit, and in the month of December, the list? Good, right? Anand has given the correct answer. Samrat, sort of, yeah. Financial year, people have got the bonus. They're making the term deposit. And again, Braj, okay. Braj is asking for a bio break. Sure, Braj. I mean, let's take a logical break at 8:30. Come back to that. Okay. Yeah, let's just proceed a little bit. Similarly, for December. So again, December is the month where people they are spending the holiday season, spending a lot, Thanksgiving, Christmas, everything is there. So not many term deposits are being made in the month of December, right? Okay. The value counts for the data that we have across different months. And then the day of the week also. I don't think that day of the week be having any kind of a significance on the term deposit. And here you can see that day of the week. So though you can argue that Thursday is showing the maximum, like typically if you see on the longer run, right, almost at par, almost on the same levels, the day of the week part, right? Let's come down. Okay. And then this particular value is where what I believe is that when they have been last contacted, right? So not many of the customers you find that they have not been contacted for very long, right? And again, this shows the number of days before which this customer is contacted. These are the numbers we have. So many customers are contacted quite very frequently. That's what we see. Okay. So what we did was with these values, we actually converted that to some categorical values. 999 or more means that they have not been contacted for long. And This one's all these other ones 3, 6, 4, 9, 2, 7, 12, 10. This means that they have been contacted recently. That's what it means. Let's come down. We have created a categorical variable. It says p days underscore cat. That's the categorical variable which is being used to indicate that whether they have been contacted recently or not. Right? How my data frame now looks like. Come down. This is the value for the p days. And not contacted, many customers are there who were not contacted. Probably contact those customers. Maybe there's a chance that they will be more taking term deposits. Right? We drop the p days because again already that p days, the numerical column, we have converted that categorical column. This is how my data frame once again looks like right now. Last thing that we are going to do before we take a break is the outlier treatment part. Remember, there were quite some data, right? The age and the charges, thing like that, which were we got the outliers. So what we are going to do is we are basically going to take the lower limit and the upper limit for these outliers. And what we are going to do is that we are going to put the threshold on the age part, right? On the lower as well as the upper bound. We are doing that outlier detection. As you can see that the lower limit is 9.5 and the upper limit is 9.5. Right? So again, if the age is greater than or equal to 69.5 and the upper limit of the age we have already seen, the maximum is 98. We are rounding it to the upper limit, which is basically my 69.5. That's what I think we're putting the threshold on. Right? Here you can see that the upper limit for my not being outlier is 69.5 and the lower limit for not being outlier is 9.5. And in all the cases, it was only the people had more ages that was coming as outlier, not this one, right? Once we do the fixing, now what happened? Now what happened? So the all term is not defined. Like term, okay. We have not run this one. Coming, run this one. Oh, we have not run this. How it should run. Okay. This one was the histogram before the outlier treatment, right? And then let's do the outlier treatment. After this, right? After doing the outlier treatment, we find that we have ensured that there are no outliers in the system, right? Okay. Come down. The campaign also, we have done the same thing. So, draw the histogram as well as the box plots. This was before the treatment, this is after the treatment. Before the treatment, after the treatment. Right? So again, we have been able to clearly come cleaning of the data. Finally, what we are going to do is we are going to create our data set. So X value, the features, and Y, the target, shape of the X value, shape of the Y value, right? Separating out the categorical and the numeric. Why? Because again, categorical and numeric, they have to be treated separately for this thing, the data encoding part. The X numeric part is the X categorical part. So there are 2 numeric columns which we are going to use and 11 categorical columns. Pre-processing the numeric data. Remember, we had discussed this, right? That whenever you are using numerical data, right, generally try to use scaling. So by the way, the scaling part of this, here we are doing this standard stress. This one, I will just can you tell me why I used the mean max scalar out here? Why not the standard scalar? Why the min max and why not the standard standard scalar? Anyone remembers? Just few weeks back only we had discussed this. Why the min max and why not the standard scalar? Because mix of categorical and numerical, correct? Great. So it is scaled, and then the categorical data, we are doing the dummification, right? This is what we have. So the numerical scaled and the categorical dummy, we are joining the two. This is my final shape. Right now, 41 columns have been created. 41 columns have been created, right? Let's probably now take a logical break. It's 8:28 if I watch. Let's come back at 8:38. What do you say, people? 8:38, should we come back? 8:38? Yes, no, maybe? Or should we continue? Raj is saying that there should be a break. 8:38. Let's come back after 10 minutes and continue with our discussion, right? So break, and let's come back at 8:38 sharp. Let's slowly come back. Project my screen. Yeah, come back. Have some time. Okay, it's 8:38. Let's get started. Let's get started. Now that I have put my data in some kind of a proper shape, let's do the Paint test split. Here we have said that the test size is going to be 20%. Tell me something. Is there anything that we are missing when we are doing this Paint test split out here? Anything that is being this Paint test split out here? Anything which we are missing when we are doing this Paint test split out here? Wonderful. Yes, Stratify. We could have actually used the Stratify out. What would the Stratify would be on? On what value we would have done the stratification? On the Y value? Okay. The Y value we would have done the stratification. So let's do that. Okay. Had we not done it, once again we would have created some kind of a imbalance in the process. Even after doing that particular oversampling, we could have the imbalance part. Okay. So how my paint looks like, and then two values 2938 and one value 3712. Right? This is what we get. This time we are going to use the new piece, which is the random oversampler. So again, this is also another library which is there. By the way, the library that we had done last time, library is a much evolved library compared to random oversampler or random undersampler. Right? Because as I said, what it does is that it actually synthetically creates some new data point, new features based on the existing features which are there. Now, that sometimes people does take offense whenever you are trying to construct kind of features based on some existing feature. See, why I'll tell you. So it's almost like in a data set, you're having, say, let's say humans, apes, gorillas, all those things, right? Whenever you're using something like a SMOT, so what it will try to do sometimes is that the human's head, it will probably put on a gorilla's body, and then probably from the legs onward, it might be that of a chimpanzees, right? That's why statisticians, they might dissuade you from using smooth kind of a techniques. They probably would recommend more using some kind of a oversampler or a undersampler. So here is this one, the oversampler we are going to use. And the sampling strategy, we say, is that minority strategy is what we are looking at. The training data, we are basically doing the oversampling on the training data. By the way, please note one thing, that all this oversampling kind of things, or again anything uh, where you are tampering the measurement of the efficiency of your models, please do whatever you want on the training data, but don't tamper with the validation data part, right? Whatever tampering you want with the training part, so we are tampering the training data only out here. Okay, the training shape, and this is how it like. Original one, it had 3712 values for 1, and this time you see there is 29,058 data point for this one. Typically, I'll tell you what happens is sometimes people also this and undersampling and then follow it with the oversampling part, right? Undersampling and then follow it with the oversampling part. See, 3,712 data points, or oversampling it to 29,238. Lot of data points will get duplicated, and that's actually creates a area whereby you can have this risk of getting into some kind of overfitting. Another strategy which people uses are that first use a undersampler and then undersample the majority class, right? After you have undersampled the majority class, and then you can use the oversampler to oversample the minority class. That's also another strategy which is being widely, right, in this kind of a scenarios, right? But again, if you ask me, it will always be better rather than dropping some data points. It will be easier. You can probably get data points up to the mark, and then maybe you can do like a k-fold cross validation where you can have more number of folds. You can always do that. That is more preferred. Randomly just dropping some data points, and some real data points we are talking about. Point in dropping real data points until and unless missing values and those kind of things are there. Okay. This, what we are going to do is how my data looks like right now. The oversampling using that SMOT, which we are talking about, which I said statisticians may not really allowed to do that. But again, otherwise, you are free to choose that whichever one you are going to use. Right? I will not execute this particular part. Let's do with this first one. Let's see the performances, and then we'll come back to this particular part. Okay. Confusion matrix, classification report, right? And then accuracy score, precision score, recall score. Okay. Let's first do a logistic regression on this. Again, we have imported logistic regression, and then we are fitting the data on this. And then here is the classification matrix. Shows that the accuracy is 0.79, the recall is 0.61, and F1 is 0.63, and the precision score is 0.29. That's what we see from this one. Okay. By the way, once again here, rather than using all this metrics here, what you can simply do is remove all this part. You can probably comment classification report is already there. Print report. Let's do one thing. Let's just classification reporting also there. So yeah, let's run it once again. Will not give an error. There's already an error. Okay, so classification is not defined. Why? Already defined this classification report. Have we not defined? Classification is not defined is what it's saying. Okay, my bad. This will be what? Fine. CL report. Okay. So here is what we get. Here is what we get. Result is not coming in a very format. It's just print CL report. Nothing. Okay. Okay. So this is what we have. For the 0 class, precision 94%, recall 81%, F1 score 87%, and this is the support value. For the 1 class, the precision is 0.30, 0.62, F1 is 0.40, and support is 928. Not very good results for the class, which is 1, right? 1 class, the people were taking this, right? In spite of doing and oversampling, right? We did not get very good results with this one. Let's try to do the same thing with the decision tree. Let's see what we get. Here is the classification report for the decision tree. Not too much of a this thing, not too much of a change, right? So earlier the accuracy was 79%. We improved a little bit. Right? But again, F1 score it went down, right? Precision and recall. See, the recall it came down significantly. So yeah, once again, not very good results is what we are getting. We spoke about something called as a grid search. Remember, grid search, it does a grid search across the different parameters. So here you see that we have fitted the parameter lists, that is the maximum depth, minimum sample split, all those things, and we are asking it to do a grid search. See that how much time it takes. Grid search will take a little bit of time, because again, it exhaustively it will go through all this depths and this sample split, right? Here though we have given some discrete values, 50, 100, 150, 200, 250, right? If it was a continuous, then you would have realized that probably have tried to evaluate. Okay, the best parameter that we are getting is maximum depth 7 and the minimum sample split 50. That's what giving the best performance. quite some time. And the classification report, let's see. Okay. I don't think there is a too much of a change. The recall has increased a little bit for the class with 1, but otherwise not too much of a change in the performance, right? Overall accuracy, if you see, it's 80%. Earlier, I think we reached 84%, right? Using the normal decision tree. But again, using this bit search, we don't think we have got too much of our optimal values, right? The values are not really actually coming very well. Lastly, we are going to use a random forest classifier. Let's run the model with the random forest classifier. And this is the classification metric, what we are going to get. Okay. So again, the random forest classifier has the same kind of, almost the same kind of accuracy of that of the decision tree that we had. But otherwise, not much of a improvement which is there. And finally, the gradient boosted modeling. I'm using a GBM classifier, gradient boosted model classifier. It takes quite some time to build the model. You're seeing it's taking quite some time to build the model. Done. Let's do the prediction. And here is the classification matrix. Let's see. Again, here it's around the same mark, but we are not being able to increase the performance by a lot, right? For the class which is 1, who we have done an oversampling, it has not really created much of a performance differences. Let's do one thing. So in the earlier part, what we had done was we had basically used a oversampler. This time what I'm going to do is I'm going to use the smoke, which basically creates new features based on the features of the undersampled class. Let's do that. Okay. The numbers and everything are going to be the same, but the result part, we should get some better result. Start the logistic regression. Fitting the logistic regression. Here was the earlier metric where the F1 score was 0.40, recall was 0.62, right? These are the two metric which I'm interested in, the recall and the F1 score. Accuracy was 79%. Let's see if it has changed this time. No, it went even further down, right? It became 77% this time. See the decision tree part. This time with the decision tree, what we see is that once again, the results are not very positive, right? Grid search. Some time. Okay. See, this time the parameter has changed. Earlier it was 7 and 50. This time it has come out as 7 and 200. That's where it has got the optimal. Let's see, it gives some better result this time. Okay. So earlier, if you see the F1 score was 0.40, accuracy was 80%, recall was 59%. Let me run this one. 59, 40, and 80. Okay. See, this time recall has increased, right? But again, F1 score came down, and the overall accuracy also has come down, unfortunately. Right? And lastly, the random forest. Almost similar, comparable. Probably the best that we are getting in this particular scenario. I'm pretty sure that GBM is also not going to give me the best model. Let's do the GBM. Time change. Hold on. The minimum sample split should have been 200 because that's what we got. Let it run. The earlier case, it was 59, 43, and 82. Let's see this time. So the overall accuracy has increased. The F1 score has also increased, but the recall value has come down. Recall value has come down. The minimum sample split, we can make it as 200, and let's see. Saurabh has a question, interesting question. Why I'm not doing grid search on a random forest or the gradient boosting model? See, for doing a grid search, what it tries to do is that it tries to fix in the hyperparameters which we are using. When you are using this XGBoost or this random forest, these are ensemble methods which are there. In any case, grid search does an exhaustive search on the model itself. And then right now you're asking me to do an exhaustive search on the model and the ensemble of it, right? So again, it will become exponentially difficult for the model to come some kind of a conclusion. That's why we are not using. The accuracy once again this time also remained at 88%, and recall 43%, F1 score 45%. That was what we have. The last thing that we are going to do is, rather than 100, is let's use the 1000. Take quite some time, but this time you should expect a little bit better model. What it is doing is internally it is creating some 1000 trees, right? Process 1000 models is what it's creating. Okay, quite some time, quite some time. You can sort of you can see that the model creation itself, it takes so much a lot of time. If you had put in the grid search on the ensemble models, said that the exponential increase is what you have experienced. As such, again, this grid search is not the best method you can do. Right? Whenever you're using grid search, what happens is computationally it takes a lot amount of time. Again, rather than use grid search, there are actually other methods like this random search CV is also there, right? What it will do is it will not go for the exhaustive search like that of grid search, but it will do some searching in some randomized pockets. It will do the searching, and from those randomized pockets, wherever it is getting the best result, that is what it will finally hold on. Right? See here, what time it is taking, just because we have increased the number of trees which are there. And by the way, this system it's running in parallel, right? We are using this Google Colab, running in parallel in the Google architecture, based on whatever has been allocated. Still, it is taking such a lot amount of time. So again, let it run. But again, essentially, okay, I think now it has got the this thing. See if we can get some better result. Probably not. So 43, 45, 88. See, overall accuracy has gone up, but both the recall as well as the F1 score, that has once again, even the GPM have not been able to get to a very good or a optimal point. Any suggestion, friends, that how we can probably make the performance a little bit better? How we can make the performance better? Any ideas? How we can make the performance better? Typically, what is happening is that the class which is underrepresented, even after doing an oversampling, have not got good results for the suggestions as to what else can we do in order to make it better. What else can we do in order to make it better? Okay. Saurav is saying get more data. Sure. Obviously, get more data. So again, when I'm saying that get more data of which particular class, which particular kind? Which particular kind of data? True. So get more data for the minority class. That is one. And also ensure that the features which are there, the features should be more varied and well represented in the data. If you have some features which are basically clustered around one particular side of the data, that is probably not the best result that you'll get. Right? Okay. This was what we had. So even with our best attempts, by doing this multiple experiments also, we were not able to improve the metric scores by a lot amount. Right? That's what we saw. Okay, questions before again we move into some of the theoretical parts. I think some people had asked for. I think Saurav had asked for. Samrat had asked for. I'll move on to those parts, but yeah, before that, questions regarding the hands-on part. I have given you pretty exhaustive kind of codes which are there. Exhaustive codes. Please again play around with these codes. Please play around. Some more experiments till you're able to get it. Samrat is asking, can we try any other technique? See, Samrat, I mean, whenever we are not getting result from model, there are two things only that we can do. One is we can probably fine tune the model more, construct variables, do some more pre-processing. Right? That is one. And the other is that we can try to reach to some kind of optimality for the models. So again, you can very well say that in most of these models which we had used, say for example, apart from the decision tree that we had used, right, where we actually tried some kind of a alignment of the optimal value. But apart from this decision tree, none of the other models we have done any kind of a hyper tuning. Right? So yeah, one of the things that you should be doing is that you can try to do hyper tuning of the model, so that you can get some better or improved. That's obviously one of the things to do. But see here, the problem was with the data. When you have data, probably not much sufficient. At that point in time, have to store some more data that we were able to get a hold of the underlying variation. Here, what we had done was we had done a train test split, right? And my data point itself was very low. So probably the kind of variations which is there, it has been well represented in my training data, but the test data probably came from a different population. In the very initially only we had done the train test split, and all the oversampling and everything we have done based on the training. Test data was got fixed in the very beginning. And you are not going to manipulate the test data, as I said, by under any circumstance. So when we had done the train test split, at that point itself, maybe what has happened is that quite a bit of imbalance. Balances were not well represented in my oversampling also. That might be one of the reasons why we have not been able to get or improve results for the undersample class. Any other thing which comes to your mind? Any other thing that comes to your mind? Any other thing that comes to your mind? Anything that we could have used so that we get better results? Anything? Anything else? For machine learning, data is very important, right? Not getting the right kind of data, however hard you might try, not get optimal results. That's a challenge or a problem. Samrat is saying polynomial classifier. But again, Samrat, I mean, how does polynomial classify solve your problem? In fact, again, we have discussed, right? Whenever we are using the ensemble kind of techniques, it can map both in the linear as well as in the non-linear space. If you are saying that polynomial classifier, I didn't get the point as to how it is going to help solve the issue which is here repeating. As such, you have used this ensemble classifiers. That will take care of all the different kind of decision boundaries which are required. Right? Okay. The hands-on part we might stop here. But what we can do is that go back where we had stopped yesterday. Okay, this is where we were, and again, this will answer Samrat's dilemma also. Samrat, if you see, this was the AdaBoost model that we had created. Probably you had left the class yesterday. Here, by original data set. And from this original data set, what we are doing is first we have split the data set in such a way that we are able to identify the negatives from the positives. And by the way, this is a very simple rudimentary classifier that we have used. That's why what it has done is it has just drawn a simple straight line, which should ideally segregate the two classes. But in the process, what has happened is a plus got into the zone of the minus, and 2 minuses came into the zone of this pluses. What I'm going to do is next time I create a sample from the data, this misclassified data will be taken with a higher probability. That's why here what you see that this data point got a more chance of selection, this data point got a more chance of selection, and this data point also got a more probability or chance of selection. But once it has happened, what happens this time is that it creates another model which is able to segregate this bigger minuses, which you see, which was not classified properly earlier. Right? This time it has been well identified, but again, because it is a very simple or very easy kind of model which it has created, it was unable to take into account these 3 points. Unable to take into account these points. So once again, all the misclassified points, this time the misclassified points are this 3 minuses, minus, this minus, and this minus. It was given a higher weightage, and this is the final classifier which I'm taking. This time also, as you see that only one of the pluses has been properly identified. This one sits on the row, but otherwise it's not doing a good job in the modeling part. But then when you are combining these classifiers, see the combined classifier from a linear space, it has actually gone to a non-linear space and perfectly able to segregate the two different classes. Isn't it? Yeah, this was covered yesterday. Yeah, I know that. I know that, sort of. I think Samrat was not there. I just repeated this particular part. Yeah, I know that this was covered. Okay. Last thing that we covered yesterday. These are the steps for data boosting. That initially all observations given equal weights. And then a model is built on a subset of the data. Model predictions are made on the whole data. And errors are calculated by comparing the predictions and the actual values. And whichever points were misclassified earlier, they are being given a higher weights so that adaptively the model starts boosting. See, it's called adaptive boosting. So at every stage in the model process, it adapts the right. So these are the adaptive boosting part. How the chart works: original data set, have a model, predict, right? Update the weights, have a second iteration of the model, predict on the weighted data, and like this, you keep on the predictions. So it's a pretty stable algorithm, the data boosting part. But again, like most of the boosting algorithms, also might get into the problem of overfitting, but more or less, as it's seen that it works pretty well and used in many areas, and it does a good generalization. And many different kind of classifiers also can be used for this data boosting part. And then the disadvantage is that, see, as such, all these models, they have a tendency to overfit. And again, if you're having some kind of a noisy data, then basically the efficiency will get highly affected by the outliers, and the solution will become suboptimal. That's with the data boosting part. And then come to the stacking part. Saurabh had asked about this stacking piece. Right? Now, stacking is a very interesting concept. What happens with the stacking part is that I think Samrat is having some question. Yeah, Samrat.
So, sir, is it the same way like how XGBoost and gradient boost also works like ADA boost? Like maybe there's some variation in which they adjust the weights, right?
See,
So
any of the boosting algorithms, at the heart of it, what happens is that the model keeps on boosting the underlying values which were underrepresented. So that is something which is inherent to any of the boosting algorithms which are there. Now, ADA boost or XGBoost, the principle of working exactly not the same. The way in which the models are getting created. But the boosting part is common for all these pieces. Again, we'll come to some of these models and then probably we can discuss once again. Okay. So coming to the stacking part, here multiple models are being placed one over the other. And rather than the original data, the predictions of the data are being passed on from model to model. Predictions of the data are being passed from model to model. We show. So here you have the training data, and then you have this classifier. Output value of the classifier is something that you take into your account. Training data classifier, output value from the classifier, and training data classifier, once again the output value of the classifier. Now with all the output values of the classifier, right? So again, this is your model 1, model 2, model 3. So model 1 output value, model 2 output value, model 3 output value. That itself becomes the input data for another classifier, and then from that the output data comes. What will happen is that, let's say for a classification problem, each of the classifier give some kind of values, right, for the output class they are interested in, and those predictions itself gets fed into a different model, which based on the predictions from the earlier models along with the target value, which by the way doesn't change, it creates this kind of task, right? We show you the training data set, right? And let's say I've split the training data set into 10 different parts, right? So like we have done for this K4 cross validation, the training data set is split into multiple parts. So a base model is fitted into the 9 parts and the prediction is made for the 10th part. So let's say that the first model is a decision tree model. It's the first model which we have created. And then based on the decision tree model which was there, we take the output from the test data as well. Right? So using this decision tree model which we have taken, the predictions are made on the test data as well. Next, on the same set of data, we take, let's say, a KNN for the training, and for the test also on the same model, we perform this KNN part. So now, this particular part actually becomes my training data, and this particular part becomes my test data. Now, based on this training data, right, this data itself, the decision tree, the output from the decision tree KNN, that is being fed another third model which is there. Right? It can be any other model, like a neural network model, or maybe once again this data itself feeding it back to a decision tree model. Like that. But typically, what happens is that since you have already considered a decision tree KNN, the other model on which the data will get fitted, a more complicated model is being used here. And then we take the prediction from that particular model, and this final model which has got created from this decision tree KNN inputs features right now, that is being used to evaluate the testing. That's how the process of stacking works. Very interesting principle. And in the case of static stacking, one of the differences is that it doesn't use a homogeneous weak learner, rather it uses heterogeneous weak learners. And then the stacking you can do actually at multiple levels, multiple layers. But all these cases, you are making the model difficult and difficult. The predictability aspect of the model that also goes down quite some extent. You're doing this multiple stacking. Stacking itself takes away the predictability away from your model. And again, multi-level stacking, but just making it more and more complex. Right? Again, when to use stacking, right? I generally won't recommend using the stacking part. Right? I generally won't recommend using stacking part because again, the interpretability from the model completely goes for a toss. Right? And also there is a chance of making some kind of a overfitted model. That's why the stacking, I have not seen many people using the stacking part. Questions? So that okay. Braj has a question. Yeah, Braj.
No, sir, actually, I just thought that the time is going off. I just wanted to understand the term and exam pattern.
Sure. We'll take that. I hope there's no quiz at 9:30 today, or there's a quiz today also.
No, there's no quiz, but we started our day at 6 p.m.
Okay. Fine. Samrat? Samrat had some question.
No, sir, I'm fine.
You're fine. Okay. So yeah, let's stop at the stacking part out here. Other models like this blending, right? So blending model. Let's stop here. Coming back to the term and exams. So let me talk about the kind of things that we have covered in machine learning model selection part, second part. We had started off with the decision tree part. We saw that okay, I mean, how decision tree you can do classification, regression. What's the notion of this splitting of the decision tree, right? How decision tree is being splitted. What is the hypertuning parameter? Some of the things which were being covered in the decision tree. So again, in terms of a model, proper model, the decision tree was the only proper model that we had, the proper base model that we had learned in this machine learning models part. Decision tree, obviously, it will form a important part of the particular syllabus. One or the other question you might expect from decision tree. The next piece that we had covered was the part with the model selection, where we were discussing that how you can make a model stable, the different ways in which a model can be selected, right? The different kind of techniques, right? The filter methods, right? The embedded methods, all those pieces is what we had discussed. From the model selection part, the important pieces which will be is that how do you do the cross-validation of the models, right? That particular part, the different notions of the cross-validations that we have covered, that particular part will be pretty important, the model validation. Also in the model validation piece, things like how do you reduce bias, variances, all that part, that's also a pretty important part, right? And see, when I'm saying that these parts are important, not only important from the point of view of the exams, but these are some of the topics that you should keep up with your repository in your learning for a considerable long time. Right? These are some things which are very popular topics for people who would like to switch careers and go for a selection or a process. Right? These are some very important terminologies or concepts for you to use. Right? Then came the third part, which was basically this ensembling technique. In the ensembling technique, we have spoken about the different kinds of possible kinds of ensembles which are there. depending on how you aggregate the result, depending on the kind of models that you use, right? Homogeneous versus heterogeneous model, right? And depending on how the models are being built, they can be built parallelly, they can be built sequentially as well. These are some of the strategies that we spoke about in terms of the ensemble method. And then we spoke about the boosting methods, right? The bagging methods, how bagging is different from boosting, right? Which one will help you reduce the bias, which one will help you reduce the variance, how can you get an optimal model. So those are some of the things that we had covered. Also, again, we covered in details part of this how to work with the imbalanced data set, how to ensure that you can balance an imbalanced data set. Those are also some of the things that we have discussed, and also we did the hands-on in the class itself, right? In terms of the pattern of questions which will come, one pattern of question that you can expect are some very small numericals based on some of the concepts that we have discussed. Very small numericals that you can expect. That is one. There will be some situation-based kind of questions where a situation will be given and you might be asked that, okay, what kind of a model you'll be using in this particular scenario, why this particular model should be used, what are the other alternative models. So that's a situational kind of pieces. The other will be straightforward questions and definitions. That's also another kind of questions that you can expect. And finally, doing some kind of a comparison. So let's say a comparison between random forest and a decision tree, comparison between, let's say, a classification decision tree via vis-a-vis a migration decision tree, right? Difference between stacking, blending, right? Boosting, bagging, right? Sequential algorithms, parallel algorithms. So those are also probably some of the pieces that you can expect in the team. Question, any coding? No, I'm not going to give any coding in the term and exams. Typically, it's going to be like a theoretical kind of paper with some bit of mathematics, right, which will be involved, and some bit of this thing, situational kind of questions. That is what I'll expect the exams. Right. Again, once again, one thing that I would request you is that please write to the point. So typically, when you write long answers, not necessarily that long answer will give you better score, better marks. You can express yourself in a short part, like if your answer covers all the significant points which are there, right? It contains adequate examples, you should be good. Also, the other thing there is that whenever you are writing your answers and the final answer scripts are there, generally what people does, I mean, the exam system at NM, what it will do is that it will run your answer against the known web links which are there. So again, if your answer has been found to be like some kind of a verbatim copy from some web links, some popular web links, or maybe there is some kind of a match answer, someone else in the same batch, probably the exam department automatically, the system flags this out, this kind of answers, and they are not sent for evaluation. I just thought that I'll just explain these things to you, that at the end of the day, you can give your best attempt and you can get the marks. See, typically, if some answer sheet, it comes under some particular threshold of matching, either with some kind of a web resource, or again, between 2 or 3 candidates, answer is matching, then typically these answers are not sent for evaluation. That someone probably had written maybe some genuine answers also, even if one or the other answer they find a match which is significantly higher, then the entire paper gets cancelled. NM is pretty strict in this particular front. Okay, that's why it's a university of excellence, right? So just bear these things in your mind whenever you are writing these answers. Right? Some of the things on which none the system has any control over. Right? It's completely guided by the exam policy, which is there. Yeah, please try to adhere to that. Try to adhere to that. You've given a lot amount of time and effort for these classes. I wish and I'll expect that all of you do very well in this term and exams. Right? Yeah. Find any other question that you're having? Okay. Nihal is asking what kind of a numericals? Numericals, like again, we had done things like your impurity calculation, calculation of all this information gain, classification error. Those kind of a calculation are some of the things that you might expect. Small things, but again, the advantage is that in this kind of questions, you won't have to write a long answer, right? Just 2 or 3 line answer you have to write, and you are generally being awarded the full marks for this kind of answers. Right? Okay. Anything else that you have? Any other question that you might be having? Any other question that you might be having? Anything else that you would like to share with me? Again, I think this particular batch, right? We also have other machine learning coming. I'm not going to take that particular part, which is the advanced machine learning, which will cover things like your unsupervised learning as well as the times. Yeah, it was great interacting with all of you. Right? It was great. As I said, that I'm not really very active on this thing, on social media and all those things. But in the slides, you'll find my email is there. If you like to reach out to me for anything specific, any kind of advice which you require in the domain of this data science, yeah, please feel free to reach out. I'll be happy to share my experiences with you guys. Again, otherwise, like to connect with on LinkedIn. Go here. What my LinkedIn is. Okay, Kavita is having this question. Confirm me about the query of whether any model with high variance and bias can coexist. I didn't get any significant results for this one, Kavita, right? But again, that there will be scenarios where you can get model with high bias as well as high variance, right? See, when we are talking of coexisting models with high bias and high variances, right? See, a bad model, typically if you're having a model with a very high bias, right? High bias in the sense only 1 or 2 data points of the model be probably rightly classified. That particular case, the variance part, mathematically, what it comes is that the variance part should also be low. See, when I'm talking about the variance part, it is about the bimodal kind of problem. When there are this thing, yeah, a problem where there are only 2 classes. In the cases where you have multiple classes, right, then a model which is having a lower bias, sorry, a high bias. So model is having high bias, so it might lead to any one of those classes, right? So let's say there are 5 classes, A, B, C, D, and E. 5 classes are there. If your model is having a high bias, in that case, the prediction can be any one of those 5 models, and it can be random also. So in that particular case, I think that your model might end up both with a high bias as well as a high variance. But again, as I said, that I have not got any good references from where I could check and confirm you this answer. The answer which I gave will pretty hold true for models with many different classes. But for binary classes where your model is having only 2 values for the output class for the target, I'm not very sure, Kavita, that whether there will be scenarios where high bias as well as high variance will coexist, right? So again, that's what I can tell. Until unless there is no proper source where I can confirm, right? It should not mislead you. But again, for problems where the target variable is having multiple classes, I'm pretty sure that a high bias model will also end up with a high variance. Right? Okay. Any other question? Any other question? So guys, nice talking to people, nice teaching you, right? Right, do very well in this particular field, data science field, right? It's a field with a lot of immense potential there in this particular field, right? Try to grow, and the best part is that it's a lifelong learning for all of you in this particular field, right? So again, I'm very happy and very excited. People put themselves into this particular fields. Yeah, that's it. All the best for your exams, right? Remain in touch, right? Good night, all. Take care. Happy weekend, and yeah, happy Independence Day to all of you.